All right, in Chapter 2, Section 5, we'll be looking at continuity, so if a function or curve is continuous or not. The first video is going to go into if f of x is not defined at c, then f of x cannot be continuous on any interval. So this is close to being correct, but the part that makes it incorrect is this right here, on any interval. So we could have a function that's going along, and then right there could be a discontinuity, which we call a hole, and that's right at x equal to c, and the y value would be f of c. Well, this is a hole, and it's a discontinuity. But the function is continuous for all other x values other than c. So we could say that the function is continuous all the way back here and then all the way up here. So it's going to go on to infinity. So this one would be false because you can have chunks of your graph that are discontinuous, and that does not mean that the entire graph is discontinuous. Okay, that's problem 1. Problem 2, assume f is continuous function if f of a is greater than 0 and f of b is less than 0, then by the intermediate value theorem there is a point c in that's an element of a, b such that f of c equals 0. So the way it's written is very math speak and it's a little confusing, so let me try to break it down. This letter right here stands for an element of. So it just means that C is between A and B is all it means. Okay, so let's say I have A over here, and it doesn't matter. So x equals A, and let's say this says f of A is greater than 0. So f of A is somewhere above the x-axis, which puts the point right here, the xy point right there. When x is A, the y value is the function evaluated at A. Then we pick B, can be anywhere, let's put it over here. And it says f of b is less than 0. So let's put it down here somewhere. Here's f of b, which means the intersection of those 2 points is right there. All the intermediate value theorem states is for a function that's continuous, I have to somehow get from a to b, and there is no way to get there without crossing through the x-axis. So that point right there is point C, and the y value for that is 0. So f of c is 0. So this is very true, and I could have drawn it in reverse. So I could have written A below the x-axis and B above the x-axis, and I would still have to draw a line that would cross through the x-axis to get from A to B, f of A to f of B. So that's intermediate value theorem with a picture, and that is correct, true. Okay, question 3, if f is continuous on negative infinity to infinity, what can you say about its graph? The graph of f has a hole, the graph of f has a jump, the graph of f has a vertical asymptote. So no, you would say it can't have any of those. So if the graph is continuous for all x values, it's going to go to negative infinity, it's going to go something like this, and go to positive infinity. But let's talk about what these other things are. See if I can draw every kind on this one picture. So what does a hole look like? We actually already kind of saw that one. A hole is just literally a gap. It's not a gap. It's just a open circle in the graph, which means at this point A, so we would basically say f of A is undefined. Okay, so that's what a hole is. Hole. Okay, and then let's say our graph keeps going. And then here it's defined, but then it jumps down to here. Okay, this is called a gap. and the function would be defined, let's call this b. It would be defined at f of b, this filled in one, and it would not be defined at this hole down here. So that's called a gap. And then let's say that the function goes down to negative infinity like this, and then it picks up on this other side at positive infinity and keeps going to the right. This vertical line is called a vertical asymptote. So this is a vertical, we've seen this before, but it doesn't hurt to review. This is a vertical asymptote. And those show up by the x value. Let's call this x equals c. A vertical asymptote occurs when I have some numerator divided by x minus c. So when x is c, I get 0 in the denominator. I get divided by 0, so it ends up being a vertical asymptote. So those are the three different discontinuities that we will see in this course. And we'll kind of see how they show up and how we can deal with them throughout this lesson. Okay, problem 3. Okay, so problem 4 says, sketch a graph that's continuous except for the stated discontinuity. So it says a removable discontinuity at 3. A removable discontinuity is basically saying a hole. So this is a hole at 3. And then they have it filled in here, so it's actually defined. This would be f of 3 down here. So that one could work. This one has a jump at 3. Well, that's not what we wanted, so this entire function is out. This one also has a jump at 3. That's not what we wanted, so this one's out. So a lot of times you can process and eliminate pretty quickly here. This one has a hole, so this one could still be in it. Okay, and then it says it wants a jump at 5. So for this one, it has another hole at 5. So we can actually process eliminate this one because we're looking for a jump. And right here at 5, this is a jump. So this one has the hole at 3 and the jump at 5, so this one is our correct answer. Okay, problem 4. All right, 5. Which of the following are continuous functions? The temperature at a specific location as a function of time. Okay, so this would be considered a time series graph where you have time on the bottom and you have temperature as a function of time on the y-axis, and depending on where you are, so let's say we're in Florida, so it tends to be around 70 degrees. And we start our stopwatch, it's exactly 70 degrees, and then it kind of goes up, and then it goes down, and then it goes up, and then it goes down throughout the day and throughout the year, something like that. That is continuous. So there's no jumps, there's no holes, there's no drastic changes. It's just going to be kind of a smooth curve that's going to kind of go up and down as time marches along. Okay, how about the second one? The temperature at a specific time as a function of the distance due west from New York City. This one's kind of a weird unit and it makes you think. So the x-axis is distance from New York City. Distance from NYC, and the y-axis is still temperature. So this is kind of weird to think about. So when we're at New York City, let's say, in summertime doesn't work great for this. Wintertime would be better because we'd see a drastic change. So let's say it's 60 degrees. And then as we go west and we start to hit the Midwest, and it might dip down and get colder, and then as we get closer to the West Coast, it's going to get warmer because we're getting those ocean currents. And so we would have something like that. I'm just making it up. But again, it's going to be continuous. So there's no big jumps or gaps. Basically, another way to think about discontinuity, the classic way I was taught was if you have to lift your pencil. So in all these graphs, I can smoothly sketch it. I never have to lift my pencil. So a hole, technically, to draw that hole, I would have to lift. A gap is definitely one where I have to jump with my pencil. I have to lift it up. And then an asymptote, clearly I had to pick up my pencil to sketch it. So that one's continuous. Okay, how about the next one? The altitude above sea level as a function of the distance due west from New York City. So this one has the same units as this one, the x-axis, but now they are changing this to altitude. So let's use h for altitude. Supposed to be an L there. Okay, so you're walking from New York City, close to sea level. As you go west, you go over some mountains, and you're going up, and then you get into the Midwest and it starts to flatten out. But let's say you get to the Grand Canyon and it goes, bam, it goes, well, it can't go. Actually, Grand Canyon might be below sea level. So it's going to have a sharp drop off. So if I have a cliff, right, and then it might go up and then come back up again. So a cliff is going to be a discontinuity because I have this sharp drop. Okay, so that one is not going to be continuous. Okay, the next one, the cost of a taxi ride is a function of distance traveled. I think we actually talked about this with the sine function that we introduced last time. So generally the way a taxi works is they have a flat fee. So let's say to get in the taxi it costs $10. And then for distance in miles, so that $10 will get you a certain distance of driving. And then if you go further than that, it's going to jump to a new price. So let's say it jumps up to $12. So let's say the first, I don't know, 3 miles gets you, $10 gets you the first 3 miles. And then for the next 2 miles, they're going to charge you $12. And then it's going to jump again. And for the next 2 miles, they're going to charge you another let's say it goes up even more. Let's say it goes up $3 now. So now they're going to charge you $15. Okay, so then this might be the way they charge in a taxi. So there's a flat rate, gets you a certain distance, then it's going to jump and jump and jump as you go further and further. So this definitely has a bunch of gaps in it, so it's not continuous. Okay, the current in the circuit for the lights in a room is a function of time. Okay, so in this one we have current, which is, we use capital I for that. And, oops, I did that wrong. Current is the y-axis. Time is the x-axis, so we're going to have time and we're going to have current in our light switch, in our lights. And so the lights are off, 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 and then we turn them on and it spikes. So let's just put, I don't know, let's just put 1 amp. So it goes from 0 amps up to 1 amp, and then it's going to, you know, we have the lights on and they're going to fluctuate, and then we turn them off. Okay, so it won't go below the x-axis there, but something like that. Okay, so this definitely has some big jumps in it. So it has these big, from 0 to 1, and a big jump, so that would not be continuous. Okay, so those are the examples, kind of the rough sketches I gave just to give you the concept. And so that would be the answer to 5. Okay, for problem 6, we have explain why the function is discontinuous at the given number a. So a is 3. So this function is a piecewise, well, yeah, it's a piecewise function, but it's not. It's got this hole in it, and then they make a jump to 1. So the function should have been x squared minus 3x over x squared minus 9. And then it's, so this is if x is not 3. And the function is 1 if x is 3. Well, that function, if you look at it, can be massaged. So you can factor out an x on top, and you can factor the bottom into x minus 3, x plus 3. And then you can say, oh, x minus 3 and x minus 3 cancel, and we're going to get x over x plus 3. Which, if you plug in 3 into this, so if you have 3, you'll get 3 over 3 plus 3, which is 3 over 6, which is 1/2. So the function, so it's interesting. If I don't cancel those two, actually let me put this. If you cancel two things like this, you have to record that x should not be 3 because in the original problem, x equal 3 causes divide by 0 in the denominator. But if you're able to cancel top and bottom, then this becomes a whole. Okay, now the value should have been 1/2, but they're saying no, use 1 instead because this function was technically not defined at x equal 3. So how does that show up? It's actually easier to look at the graph probably. So the correct graph is right here, the bottom right one. And so what we see is at x equal to 3, you should have had 1/2 in the y, but it's a whole. And then they filled it in at y equal to 1 right there. So it's like, okay, we've got this whole, and so we'll fill it in at that y is 1 at that x value. Okay, now that's fine, but what is it asking? It's saying, explain why the function is discontinuous with a given number. So it's discontinuous because, okay, the limit of this would both go to 1/2. So from both sides, the limit as x approaches 3 of the function equals 1/2, but f of 3, the function evaluated at 3, is 1, the filled in dot. And these are not equal. Because those are not equal, we say the function is not continuous at that x value. So because of this, f of at the value of x equals 3 is not continuous. Okay, and that's what, if you look, I clicked here, f of 3 is defined, and the limit is finite, but they are not equal. So that's why it's discontinuous. And, you know, to get this picture, if you wanted to, you could go to Desmos, like I've shown you, to quickly kind of get that, to know that this is the answer, and then it's a lot easier to analyze this once you have the picture in, to be able to analyze it. Okay, problem 7. Locate the discontinuity of the function. So we have y equal to 1 over 1 plus e raised to the 2 over x. So generally, the most common discontinuity is when the denominator equals 0. So what we can do is we can say set the denominator equal to 0. And we're going to subtract 1 from both sides. And then, it's probably been a while, but to get rid of this e, what you have to do is take a natural log of both sides. So you'd say take the natural log of this, but then I have to take the natural log of this side also. And natural log is not defined for negative numbers. So if you have natural log of some value, that x has to be bigger than 0. Not only does it have to be positive, but it can't even be 0. So this right here is undefined. Which means, another way to think about it is, this right here, you can try it with your calculator. There is no x to make that, e to the 2x, to make this negative 1. So if you pick x as positive, you still get a positive value for e. If you pick e as negative, you'll get a positive value for e. So that right there is always going to be positive, so you'll never get negative 1, so you'll never get this to be equal to 0. So this denominator will never equal 0, which makes us think there's no problem. This whole thing will never equal 0. But there is a problem with this term as it is right here. If that x is 0, we have a problem. So you can try this. Type e on your calculator, raised to the 2 divided by 0, you will get an error. So we can't do that. You can't divide 0 into 2, therefore you can't take the exponent of that number. So the problem child is x equal to 0. And again, you can go to Desmos or pick x values and get numbers. If you plot this, it will look like this one right here. And at x equals 0, you can see that gap or jump. Okay, so x equals 0 is the problem number, and it shows up as a gap. So that is the problem with that one. Okay, it says, problem 8, use continuity to evaluate the limit. It says the limit, let me write it bigger so we can see it, as x approaches 4 of x times the square root of 32 minus x squared. So the first thing you should always try is just plugging in the number and see if it'll work. So we're just going to take 4 and replace that x and replace that x with 4. So we're going to get, this is the limit as x approaches 4 of 4 times the square root of 32 minus 4 squared. Let me not keep writing the limit just to save time. So this is 4 times the square root of 32 minus 16, which is 4 times the square root of 16, which is 4 times 4, which is 16. So that whole thing will reduce to just the number 16. I mean, technically I should have written limit the whole way. So limit as x approaches 4 of 16, that whole thing equals 16. I think I showed this rule before. If you have the limit as x approaches a of a constant, it just equals that constant. So we're using that rule for that after we plug in the number. Problem 9, very similar, except we have trig functions, so might have to review our trig a bit. The limit as x approaches pi of 4 times the sine of x plus sine of x. So again, we're just going to take pi and plug it into that x and plug it into that x. And you're going to make sure your calculator is in radians. Or you might just know, or unit circles, how I would have done it, that the limit as x approaches pi of 4 times the sine of that x is now a pi, plus sine that x is now a pi. Well, from unit circle or from your calculator, sine of pi is 0. So this whole thing becomes 0. So then we're left with the limit as x approaches pi of 4 times sine of pi plus 0, which is just pi. But by the same notion, sine of pi is 0. So we get the limit as x approaches pi of 4 times 0, which is 0, that equals 0. So limit of a constant is a constant. So we get 0 right there. Okay, last problem. For what values of x is f continuous? So it says f of x equals 0 if x is rational, and it's 7 if x is irrational. So in essence, this thing, so irrational numbers are things like e raised to pi, or pi itself actually, or square roots of numbers that don't terminate, their decimals just keep going. So basically, I mean, for most of these numbers, x is going to be 0. So this thing's pretty much just going to be a line like this. So I definitely can't say it's discontinuous at 7. Or, oh, for what values of x is continuous? So at 7, I mean, probably. Minus 7, probably. If x is 0, probably. X in all real numbers, probably not. So the best answer is none of these. So there's really, there's not enough information, basically. So we couldn't, we'd have to know a little bit more about the actual domain they're considering here to do this problem. So that will cover section 2.5.